Welcome back. Let's do another example with derivatives. Here I've got a function, f of x is square root of x squared plus 1, and I want to find all the points where the tangent line to that curve is horizontal. So first thing, same as before with the previous problem, I'm looking for all points, so that means I'm looking for x and y coordinates, and I'm looking for places where the tangent line is horizontal. If we're thinking about horizontal lines, we know that that means that the slope is 0. In other words, you want to find out where does the tangent line have a slope of 0, or in other words, you want to figure out where is f prime equal to 0. So that's our ultimate goal here. We need to find where is f prime of x equal to 0. And then once we've done that, we can figure out what the y-coordinate for those points are afterwards. Of course, to do any of that, we're going to need to start off by first finding out what is our derivative. And as always, we begin by using limits. So here, if I'm looking at the derivative of f, our f prime of x, that would be the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. And now we'll do the same sort of thing that we did before, which is f of x, that's my original function as given, x squared plus 1. F of x plus delta x, that's me replacing the x's with x plus delta x in the original function. So instead of x squared, I'd have x plus delta x squared. Okay, and so right away I can see that if I try to evaluate this limit, I'll have, if delta x goes to 0 right now, I'd have root of x squared plus 1 minus another root of x squared plus 1. I'd have 0 on the top, I'd have 0 on the bottom. I would have something indeterminate. So my plan here is to think about what I can do. And for the last one, when it was a rational function, making common denominators or thinking about that might be reasonable. For this kind of a function, though, it involves square roots. So I might be thinking about maybe using my technique of rationalizing. In this case, if I rationalize the numerator, if I get rid of the roots in the numerator and move them to the bottom, that hopefully might do some nice things for me where I'd be able to hopefully cancel out that delta x that's causing me my problems. So my plan here is I'm going to multiply top and bottom by the conjugate. So in the top, it's originally one root minus the second one, so I will multiply by first root plus the second one. So x plus delta x square plus 1 square rooted plus x square plus 1. And I'm going to do that on both the top and the bottom. And same sort of a thing as before, I'm not going to expand things on the bottom at all. I'm just going to leave it as delta x times all of this business. Because again, my problem was that the delta x that I originally had was giving me 0 in the denominator. I'd hopefully like to get rid of that delta x at some point, so it makes sense to leave it separated from everybody else. So the bottom, I'll just leave that as delta x times first root plus second root. Now in the numerator, on the other hand, if I took root minus root and multiplied it by first root plus second root, I know that I'm just going to get that first root squared, or in other words, the square root is now gone. minus the second root squared. In other words, the square root is gone. Here again, I'm going to be kind of cautious. You'll notice here I am subtracting. And right now, if I'm subtracting, I want to make sure that I subtract that entire root that's being squared. So not just subtracting the x squared, but also subtracting the 1. So here again, I'm going to use brackets to make sure that I'm a little bit safe with what I'm doing. Okay, so I'm going to do a little bit of expanding here, and I can see that in the numerator, I have some expanding to do. I have that x plus delta x all squared. So we'll do that. If I were expanding that, I'd have x squared plus 2x times delta x plus a delta x that's being squared. And then there's still the plus 1, and in the rest of the numerator, I am going to carry that negative through that bracket now. I have a minus x squared and a minus 1. Okay, and the denominator, I'm just going to, again, leave it as is. You might be saying to yourself, why am I not expanding that x plus delta x squared that's in the square root here? And the answer is, I don't know where my denominator is going to go. I know the numerator needed to be cleaned up, hopefully so that I could start canceling things out with that delta x that I had in the bottom. But I have no idea where the denominator is going to lead me, so I don't know if I need to bother expanding this yet or not, so I'm leaving it for now. If I do a little bit of cleaning up right here at this line, I can see that I've got some good things going on for me. I have x squared and a minus x squared that will cancel, so that's kind of good. I've also got a 1 and a minus 1 that will cancel. So again, that's also good. So I'm just going to now rewrite what I've got. So in the numerator, I only have 2x delta x and a delta x squared. And in the bottom, I've got a delta x, again, times those two roots that are being added. So if I'm looking at this, I can see that right now I'm pretty much in a good position because for the numerator, I have two terms, both of them involve delta x, so I'll be able to factor a delta x out of everybody in the top, cancel it with the delta x that's in the bottom, and then hopefully evaluate my limit after that. So I'm going to continue on and do my little factoring and canceling on the next line. So I will have in the denominator, I'll keep that same as I had before, which was delta x and then first root plus second root. And in the top, once I factor out my delta x, I'll have left behind 2x plus delta x. And now I'm ready to go. My delta x's can cancel. And once they do, things are no longer indeterminate, no longer 0 over 0. If I let delta x go to 0, then in the numerator I'll have 2x. And in the denominator, I'll have root of x plus 0 squared, which is x squared plus 1. And I'll have another root of x squared plus 1. If I were to clean this up a little bit further, I could say that we really have 2x over 2 root x squared plus 1s. Or the 2's could cancel, and I could say really I've got x over x squared plus 1. And there we go. We've got our derivative, which, again, is only part of the work. Remember, for these sorts of questions, and this is going to be a running theme throughout a lot of calculus, there may be multiple steps that we have to go through. And so we shouldn't get too excited about having finished something and think that we're done. We need to go back and remind ourselves, what was the question? What were we trying to do? Right now, all we've done is found our derivative, found f prime, but our first question really was to find out not just what the derivative is, but where is it equal to 0? So now we'll tackle the real problem. We need to find out when is f prime equal to 0. So I'll do that in green, and I'll say we're going to now solve for where is our derivative 0, or in other words, where do we have horizontal tangent lines? So I would have, and I realize I didn't draw my square root there. Shame on me. I canceled the 2's and got so excited with canceling 2's that I forgot to write the square root sign down. So if I'm letting my derivative be equal to 0, then I'll have x over root of x squared plus 1 equals to 0. And I know for fractions are only ever equal to 0 when the numerator is 0. So I only have one x value. That's x is 0. And now I can find out what the point is. So when x is 0, what's the y value? And the y value, again, we don't get it from the derivative, we get it from the original function. So if I wanted to know what is the y value when x is 0, I want to know what is f of 0. So I put 0 into my original function. So square root of 0 squared plus 1, which is 1. So it turns out there is only one point, the point 0, 1, and that's the only point where our slope is 0. Or in other words, that's the only place where we'll have a horizontal tangent line. Now, we've talked about continuity in the past, and that was one discussion about describing curves, that they are continuous if we have at every point in the domain a limit, and if we have that the left limit and the right limit agree and they're both equal to the value at that point. So that was continuity, which meant in terms of a picture that our graph or our curve could be drawn as a one smooth curve with no breaks and no jumps. We have to talk about the other concept here, which is differentiability, which is going to be related to continuity, but it is different. So when we're talking about differentiability, we're talking about the ability for us to find the derivative. Differentiating, that's the verb that we use for finding the derivative. If I say differentiate f of x, I'm saying find the derivative of it. And for you to be differentiable, for a function to be differentiable, then your limit needs to exist, the limit for that difference quotient as delta x gets to 0. But of course, you know that if you want that limit to exist, then from back in chapter 1, for a limit to exist, there has to be a left limit and a right limit, and they both need to be equal to each other. So if we're talking about the left limit, the limit as delta x approaches 0 from the left of the difference quotient, we call that the derivative from the left. And for the right limit, we call that the derivative from the right. So if you're looking for a derivative to exist at x, then you would need to have the difference quotient, the limit as delta x approaches 0 from the left and from the right would have to exist, and they'd have to agree with each other. Now, some good news, if you have a function that's differentiable, automatically it must be continuous. Unfortunately, the reverse is not true. So every function who is differentiable will automatically be continuous, so good for us, but if you're a continuous function, you're not necessarily going to be differentiable. And here's a couple of easy examples. One is sort of maybe not a surprise, and one will be maybe a bit of a surprise. The first one that shouldn't be a big surprise is something like our cube rooting function, y equals cube root of x. And that shouldn't be a surprise if we're thinking about the graph of y equals cube root of x. Remember that if you're thinking about drawing tangent lines to curves, the slope of that tangent line is the same thing as the slope of the curve, is the same thing as the value of the derivative. And as it turns out, for the cube rooting function, as x goes to 0, the tangent line that we would have there would be a vertical line. And vertical lines don't have slopes. Vertical lines have undefined slopes. So if the tangent line has an undefined slope, then that means the derivative has to be undefined as well. So even though cube root of x is a lovely continuous function, unfortunately there is no derivative when x is 0, which means it's not differentiable when x is 0. The other one, and this is the one that's maybe a bit of a surprise, is going to be this absolute value function. So as we can see, one of the reasons why you might not have a derivative might be the tangent line happens to be vertical. But another reason why you might not have a derivative might be because of the existence of sharp corners. So we know the graph of absolute value of x looks kind of like a letter V, and we have not any sort of smooth, rounded curve at the bottom, but we have a very sharp point. As it turns out, that existence of that sharp point is going to mean that we're not going to have a derivative for the absolute value function when x is at 0. So let's actually show that. So let's find our derivative at x equals 0, or try to rather, and we're going to use the limit definition to let that happen. One thing that we're going to notice here is that if you're thinking about f of x and f of x plus delta x, right now my function is written in terms of the absolute value symbol, which is going to make things actually a little bit difficult for me, because if I think about my difference quotient, f of x plus delta x would be the absolute value of x plus delta x. F of x itself would be absolute value of x. It wouldn't be super easy for me to go about cleaning that up, one thing minus the other. I can't just ignore the absolute value signs. But one thing I could do is to use an alternate definition of my absolute value function. Remember that for f of x, you could rewrite the absolute value function as the following, as a piecewise defined function. F of x is equal to x. In other words, it gives you the original input back if you give it something that's 0 or already positive. And f of x, the absolute value function, will give you the opposite. It will change the sign, and it will do that if x happens to be negative. Okay, so since f of x is doing two different things on either side of x being 0, if we were looking for the derivative of x being 0, then I would have to be wondering what's going on with delta x, right? Because remember, our whole idea of finding our tangent line was by starting with our point and a second point and bringing those 2 points closer together. Now, if I'm talking about on the right side, then I'm talking about when f of x is just equal to x. But if I'm talking about delta x being something negative, if I'm happening to be looking at my second point being on the left, then we're talking about that second part of the definition. So here, when I'm looking at my limit with my difference quotient, I won't be able to just look at what happens as delta x approaches 0. I'll have to look at what happens when delta x is approaching 0 from the right, and what happens when delta x is approaching 0 from the left. In other words, I'll have to look at my derivative from the left and my derivative from the right and see what I get. So if I'm looking for my derivative from the left at x equals 0, that's the limit as delta x approaches 0 from the left of f of 0 plus delta x minus f of 0 over delta x. So now I can do a little bit of cleaning up here. If we're approaching 0 from the left side of things, so in other words, if we're talking about negative values going into our function, then the absolute value function changes the sign. So f of 0 plus delta x should be the negative of 0 plus delta x. And f of 0, well, we can evaluate that directly. Absolute value of 0 is 0. And now we're almost finished, because if I clean things up on the top, all I'll have is negative of delta x. And on the bottom, I'll have delta x. And I'll wind up with the delta x's canceling. And I'm looking for the limit as delta x approaches 0 from the left of negative 1. And here there's no more delta x's, so it looks like my limit is just going to be negative 1. I'm just going to point out here before I do my derivative from the right that this shouldn't be a big surprise, right? If we're thinking about our graph of y equals absolute value of x, and if we're talking about the derivative, or in other words, we're talking about slopes, the slope on the left side of 0, it's always negative 1. So the fact that my derivative from the left is negative 1 should not be a big surprise. And in fact, you probably have already figured out what my derivative from the right is going to be. But let's actually do the work and clean that up and show then that the derivative from the left and the right don't agree. So we've got our derivative from the left being negative 1. Let's do our derivative from the right. So that's the limit as x approaches 0 from the right of f of 0 plus delta x minus f of 0 over delta x. And for this one, since we're talking about approaching delta x approaching 0 from the right, then we're talking about 0 plus delta x being some sort of positive number. And we know for the absolute value function, then it won't change the sign, it'll just keep it as is. F of 0, that's absolute value of 0. I'll have delta x over delta x, which will cancel and give me 1. And so my derivative from the right is 1. And so now I can answer the real question. The real question that we had was for us to show that f of x equals absolute value of x is not differentiable at 0. And the reason it's not differentiable is because the limit from the left and the limit from the right don't agree with each other, which means the limit does not exist. So I can say, since the left and right hand limits don't agree, f prime of 0 does not exist. And that's, of course, that fact that we knew from limits. For a limit to exist, the left-hand limit and the right-hand limit would both have to exist and would have to agree with each other. And in this case, for my difference quotient at 0, the left-hand limit and the right-hand limit don't agree, which means my difference quotient, the limit as x, delta x goes to 0, does not exist.